Welcome everyone. Today we're going to be having an introduction to electron backscatter diffraction, or EBSD for the acronym. I'm Chris Butcher. I'm one of the technical staff at the Canadian Centre for Electron Microscopy, which is the national center in Canada. So to start, let's begin. So we are talking about backscattered electrons being used to produce a pattern which can be interpreted, and we can get phase information and other sorts of general microstructural information, both qualitative and quantitative, using the scanning electron microscope. It is possible to do it in a TEM with the right equipment, but there aren't very many examples of that. So we're using diffraction patterns, which, if we go back to the late 20s, Kikuchi, a Japanese scientist, using a system that produced electrons of high energy, was able to look through a piece of mica, so transmission, electron microscopy, and get patterns showing information about the crystal structure. Today we also do both reflected and transmitted EBSD. When we're actually looking at samples, what's very critical is the surface preparation, because we're looking at the top 20 to 50 nanometers of the surface. So once the backscattered electrons sort of go to a deeper depth than that, we're not really getting sort of direct reflections or transmission of the actual unit cell of the material. So we are concerned today about talking about looking at crystalline materials, because those are the only ones that we get defined patterns from the unit cell. And with the advent of various technologies, such as improved computer processing and things like that, we can now do sort of automated collection and identifying or indexing of these electron diffraction patterns, or Kikuchi patterns. So why do we do EBSD rather than something like X-ray diffraction or transmission electron microscopy? Electron diffraction has better resolution than X-ray diffraction. Also, we're only getting it from an area very close to the surface of the sample. So we don't get sort of an averaging that we would get with X-ray diffraction. Also, because we're in an SEM, we can also select the areas that we want. So we can do sort of we can do submicron accuracy and selection of these areas. We can also, when it comes to talking about the benefits of doing this instead of TEM, we can also do large areas of analysis. So you can do things with large area scanning and doing mosaics of the data. You can collect fairly large areas. So this is quite often done in geology. And quite often the sample preparation is much easier than TEM, but that's not always the case. So it can be used in a lot of different circumstances. So we are concerned just with crystalline materials, but there's a lot of different industries and in academia where we actually use this technique. So you may have things where you're looking at like pipelines. It could be turbine blades from the power industry. It could be components from the nuclear industry. It could be microelectronics, solar panels, that sort of thing. You can even look at ice if you have it properly chilled. And in certain cases, we can look at organics and polymers. I've looked at quite a lot of different things. I've even looked at shells and bone for EBSD. And we can get a lot of different sort of information from EBSD. So things about grain size, information about boundaries, so grain boundaries, twins, things like that. We can also look at the general sort of texture of the material or localized texture, recrystallize and deform materials. You can look at the subgrain structures, phase distributions and identification. You can also look at the relationships between the grains and phases and the sort of strain state of the material. Now, generally, we refer to the EBSD system as having a detector. But in actual fact, for most EBSD systems, there's actually a camera involved. There is an exception to that now. EDAX does make a direct electron detection system, which instead of using a phosphorus screen and a camera, it actually directly detects the backscatter electrons, which are used for forming the pattern. So there's different setups. Here you can see our older field emission 7000, which at the back has a CCD EBSD detector or camera. We will be having another EBSD system on one of our FIBs, focused ion beam machines. The Symmetry 2. Instead of having a CCD, it has a CMOS camera. So if we look at what actually is happening in the SCM when we're doing EBSD, we have a beam coming down and hitting a sample, which we've tilted to 70 degrees. And I'll explain later as to why we tilt it to 70 degrees. And these backscatter electrons, because they're elastic collisions with the sample, are bouncing onto the screen here and producing patterns based on how they're interacting with the unit cells in the material. The background of the pattern would be the sort of noise from the other backscatter electrons, or other electrons which are hitting the phosphor screen and not producing a pattern. So we usually will tilt the sample using either the stage or we might have a pre-tilted holder. Sometimes it's a combination of both. In this case, we're doing normal or reflective EBSD. There is a transmission EBSD, which we'll talk about later. We have to insert the detector in to an optimum distance in order to collect the pattern. So the closer we are, the more signal we get. But the actual detector insertion distance does have an effect on what you see on the phosphorus screen here. And it is being captured by a camera in the back here. We can also use EDS, so energy dispersive spectroscopy of X-rays, to also collect X-ray information from the sample at the same time, which it can be useful, especially when you're trying to sometimes identify an unknown phase. So there are also some diodes at the top and bottom of the EBSD phosphorus screen. These diodes will detect the backscatter electrons, or BSEs, and you can get different contrast mechanisms. So one of them is average atomic number compositional contrast. Another gives you topographical and orientation contrast. So the actual orientation of the unit cells will yield a different contrast mechanism on things. So here we have some tungsten carbide particles, which are quite hard, and a nickel matrix, and over here we have some steel. So different levels of polishing have led to some topography, but it's been polished well enough that you actually can see the orientation contrast of the sample. Now, the patterns on the Foster screen are formed by the backscatter electrons interacting with the screen. So what's happening here is if we have the BSEs diffracting according to the Bragg condition, we get a pair of cones formed. So if you look at the bottom illustration, you can see there's a red and a beige cone here, which represent the diffraction coming off the particular unit cell we might be looking at. And the blue line represents the diffracting plane. So based on these cones will form the edges of these bands. And because you'll get the beam hitting the surface and interacting with different points on the unit cell, we will get these different bands being formed, which get projected onto the screen. So if we're actually looking at what we get on the screen, we get an image, which is basically like on the globe, a spherical projection onto a two-dimensional surface. So in this case, you can see that towards the outer edge, it's a little more blurry because we are a little further away and we're not getting quite optimum collection from the edges of things. This represents a model of the unit cell. You can see the sort of face-centered cubic material square cubic unit cell at the back. So the bands that make up the pattern are directly related to the planes in the crystal lattice. The width of the bands is a function of lattice spacing. The width can also be affected by other things, which we'll talk about later. The angles between the bands are also related to the angles between the planes and the crystal lattice as well. So with this sort of information, you can figure out the orientation of the unit cell, and also you can figure out what phase it actually is. So, and these sort of width and interband angles are unique to a particular phase. And the bands tend to represent a family of planes. Now, one of the things that's important when you're doing EBSD is quite often you want to relate the information you're gathering to the samples. So we're talking about things like where we're collecting from the X, Y, and Z planes of a surface. But we might want to relate it to if we're looking at, say, a rolled material, the rolling direction, transverse, and normal directions. So we need to know what the sort of relationship between those different sort of coordinate systems is. And we may, for the analysis, want to relate it also to the crystal sort of structure, so the planes within the material, or the direction in which the texture is going in the material. So now there's also a microscope detector coordinate system, which usually should not be part of causing any sort of concern, because usually when you do the initial sort of setup of the system, that will be corrected for. Now, when we're talking about orientations and misorientations, the data we're collecting is orientation data, and we're going to be expressing it in Euler angles. But we also make use of things like Miller indices. We also look at comparisons of different points of orientation, whether they're adjacent or not adjacent. And we need to find these sort of angles or misorientations. We'll also look at boundaries, which are basically points between points of orientation. So we may be looking at angles and axes of misorientation. So if you're looking at sort of the Gauss texture from brass, there is also an equivalent Euler angle set up for that. So Euler angles are ways of defining orientation. So it's we're using a system according to Bung. So we're doing some rotations, sequential. So we're doing a rotation about the z-axis, then the x-axis, then the z-axis again, in order to define an orientation for the data point that we've collected from the unit cell. Now, when we're collecting data points, the point itself will be whatever sort of resolution we have based on the microscope. But we will use a step size to set up the distance between our data points, and we'll set up an array of data points in order to collect the information about the material. So for each sort of data point, we'll have a pixel to represent the information that's captured, and we'll color it based on crystallographic orientation. Now, in the cases where we have data points of different sort of values, we may have a boundary between them, which we can define based on sort of misorientation and other factors to actually define things. So here you can see that the blue areas all have this diffraction pattern or Kikuchi pattern. Red have this, and the green have this. So with that information, we can define how things are going. So now, if we're talking about the spatial resolution of things, when we're doing EBSD, generally what the limit is overlapping patterns. So because we're looking at a certain interaction volume, if we get more than one pattern present, it's very difficult sometimes to separate the two patterns and determine actually what's there. It's also affected by the interaction volume that's produced by the SEM and the conditions that we have. So the interaction volume is affected by the accelerating voltage, or kV, of the SEM. The material's average atomic number, probe current, beam size, focus, astigmatism. It can be affected by charging. Also, because sometimes we're dealing with very small step sizes, it can also be affected by mechanical drift. So don't use tape to stick down your sample. And you'll notice here at that in the y direction, the interaction volume is lengthened because we're doing 70 degrees of tilt. Now, for angular resolution, the absolute value probably is around 0.5 to 2 degrees. Relatively, you can get down to fairly small angular resolutions, but it depends very much on being able to sort of accurately determine the bands. The actual image that's produced by the camera is sometimes not very strong, not a lot of signal. You may have blurring in the bands for various reasons, such as poor preparation, or there might be lots of deformation in the material. So it becomes more difficult to actually figure out exactly the pattern center, sorry, the center of the bands. You can also get geometrical fluctuations for the diffraction. The calibration may not be exactly right for things, so you may have problems. And the position of the sample versus the camera and the beam may have some effects on what you're seeing. So what sort of process are we doing when we're doing these pattern collection? So the automated process, we would capture a live pattern. We'd subtract a background. We would run it through a Huff space transformation to detect the band. So convert it to points, which we then determine where the actual bands are. We would then index the pattern or identify the phase and orientation. With a matching crystal structure we may have in a database, or we may use a model for which we've determined some reflectors that represents the crystal planes. We may do it in conjunction with EDS, because sometimes we may have something of similar crystal structure, but it may be difficult to determine which crystal structure is which. So you might have, for instance, something like iron oxide and austenite, which have sort of similar crystal structures. So you may have to have EDS used in conjunction with EBSD in order to differentiate the two phases accurately. We then collect the data, which most people find surprising, is that quite often we just throw away the EBSD pattern as soon as we're collect it. So you can have the option to save it. One of the problems with doing this is you can make the data set quite large in size. The largest I've ever had is 500 gigabytes. It took about a day to take off the computer. So something you have to keep in mind, whether you want to spend half an hour waiting for the file to open in order to analyze the data. But yeah, save the data to a file that you can then do some processing of the data later. And then we move on to another area, or we move the beam to the next point of data collection. Now, when we talk about the Huff space transformation, it's a sort of sometimes referred to as a butterfly filter. We take the pattern, and from the pattern we determine spots. So you can see that we have a particular line here of spots. And using that, we can figure out the bands within the pattern. And from that, we can see here the zone axis where the intersections of these different bands are. So these bands will actually represent a plane within the material. Now, we need the sort of crystal information in order to create reflector files so that we can actually identify which bands are which. So if we look at our unit cell here and the various reflectors that are produced, the blue reflector here corresponds with a particular reflector in the database, so we can identify the actual spacing and the family of planes that it's actually from. So, and thus we can identify, because those are unique to particular phase, the phase, and because we can identify multiple bands, we can figure out the orientation of the material. Now, when we're doing collection of the pattern itself may not be terribly great from the camera. So the live pattern, we may also see that there's some artifacts from the phosphorus screen as well. And we want to subtract a background in order to get a much clearer pattern. The subtraction will also correct for intensity changes as well. So it's a little easier to sort of see a little further out on the thing. We can also do averaging, where we can collect a number of frames of the pattern and average them to improve the pattern as well. But this increases the time for pattern collection by the number of frames you are collecting. Now, if we use different KVs, it does have an effect on the bandwidth that we're collecting, and you have to tell the system what KV you're using. Otherwise, it won't do a proper correction for things. And you can see that at 20 kV, we get a much larger area than we do at 5 kV. Also, at 20 kV, we're going to have a lot more signal than we are at 5 kV. So you're going to have to collect for a lot longer at 5 kV to get a similar brightness or exposure pattern. If we're looking at why we use 70 degrees of tilt for collecting the patterns, you can see here the effective tilt versus kV. Not many SEMs go to 40 kV. We don't have one, but this shows you an example of what effects things would have. You can see that maybe a slightly lower angle at lower kV may be a little bit better. But generally, we're working at 70, so it seems to work with all the sort of KVs. And generally, 20 kV is what most commonly is used for doing EBSD. So we can collect a nice pattern at 70 degrees. The amount that the camera is inserted will also have an effect on our bandwidth and our field of view. So you can see that the closer you are, the larger sort of area you can see. As you get further out, also your exposure time will increase as you go out because we'll have less backscatter. So these are things that can be used to look at the patterns. Another thing that can be done is binning. So you can actually combine the array of pixels in the camera to capture a lower resolution image much faster. So you can sort of go from at 1x1 binning, where 1 pixel in the camera is 1 pixel in the image, to where you have an 8x8 array of pixels in the camera. You can go from sort of a 200 millisecond exposure per pattern to a 3 millisecond exposure down here. So can quite speed up the collection of data. And we're still able to analyze this pattern and figure out the phase and orientation. There's enough information here for the computer to calculate that for us. Another thing that can be applied is we can apply gain to the camera to further reduce the exposure time, but at the expense of more noise. Now, the data we're actually collecting, once the patterns have been analyzed, it'll assign a phase, It'll have a position for that data point. It will have the Euler angles it's determined for the particular pattern. In the Oxford system, you get a value called MAD, which is the mean angular deviation from what we have in the database to compare it to. And we also have some pattern quality measurements, which are band contrast and band slope, which can be used for determining certain things like martensite versus ferrite content, things like that. But these are sort of collected before we actually analyze the pattern. Those are based on the actual pattern properties itself and the number of bands that are actually were detected for the analysis. Now, topography causes a problem when we're doing EBSD because the backscatter electrons are basically have elastic collisions and interaction with the material. So if we don't get the backscatter electrons bouncing off and going into the actual camera, we will run into sort of problems in actually collecting any patterns. So we may get a very low yield of patterns from a very rough surface. So we may only be able to do spot analysis to determine sort of the phases present. What you may see in the pattern itself, you might see you lose some of the pattern due to shadowing, and it becomes sort of poorer due to this sort of shadowing effect. You have to remember we're tilted to 70 degrees, so things that are sticking out above the area you're looking at will affect what you actually collect. So with the advent of FIB, we can now do collection of volumes of material. So we can collect slices as we FIB down through a material. In this case, we're looking at some nickel. You'll see that nickel is quite often used in EBSD for standards as an example of things. It's usually something we can prepare very nicely, and also exists in fairly large grain structures and also nano grain structures as well. So it's usually a fairly nice material for testing out EBSD systems. Now, as I talked about before, we can also do transmission EBSD. So in this case, we're not having the 70-degree tilt. We'll be maybe at 15 to 20 degrees of tilt. And we're actually having the beam go through and diffract onto the screen here. So if we look at the little point up at the top here, it's actually here we can see a FIB grid. And the little spot that's there is what we're actually looking at for EBSD. So if we can get this fairly close, we can get fairly high resolution, then much more than we can get with reflected EBSD. And also because we're doing transmission, we're not having as many problems with sort of overlapping patterns. So we can get ultimately better resolution on things, because usually we're looking at samples that are electron transparent. So you may have things in the 20 to 100 nanometer thickness range. So we can get a fairly good idea of very fine structures in the material. And it's referred to as transmission Kikuchi diffraction, or TKD for short. I'll show an example of that in a few minutes. Next thing we'll talk about is sample preparation. So this is the bane of all people that do EBSD. It is the most critical thing. It causes the most problems in data collection, is getting a properly prepared sample. Now, this probably is a subject more on its own, so I'm just going to talk about it briefly, the sort of things you can do. But you want to be able to create a pattern that you can collect fast, that you're going to be able to actually see the bands, or that the computer will be able to see the bands so it can identify the crystal structure. You also have to consider when you're doing the preparation, has it caused any effects that have affected seeing the bands? So has it produced oxides? Have you got contamination from the preparation? Sort of like colloidal silica, that sort of thing. So you have to sort of keep those things in mind when you're doing preparation. Another thing that's important when you're doing preparation is how the sample is going to be going into the microscope. So you may be able to clamp it. It may be in a plastic puck. And the position of the sample in the plastic puck will affect the sort of resolution that you're going to be getting. So if the sample is in the middle of the puck, it's going to be further away from the pole piece, so you're going to have a longer working distance. So the electron beam is going to be traveling a longer distance in order to get an image, so you're going to have less resolution. You may have less electrons depending on the situation. So you have to also keep that in mind as well. Also, you don't want to cut the sample and introduce a lot of damage that you can't remove during the preparation, or have poorly removed during the preparation. So sometimes we'll be lucky. We might be looking at, say, things like thin films or nanostructures where we're just going to look at it as received. Quite often we'll do some form of mechanical polishing, but to really sort of achieve a nice surface, we're usually doing a combination of chemical and mechanical polishing, so use of colloidal silica. There's a technique where you can do vibratory polishing, which yields very nice surfaces, better than normal colloidal silica polishing. You may do chemical polishing and etching. The problem you run into with etching is you might get topography. Electropolishing, a lot of materials you can electropolish. It is more suited to things that are not multi-phased, because you do tend to get etching sometimes because of different dissolution times for things. Ion milling, so we're talking about fib and using things like argon for milling away material. You can also use it to etch the surface as well. So the milling will leave some artifacts, which I'll show you in a moment. Also, the material may be brittle enough that you can fracture it, or you might do it in liquid nitrogen, for instance, in order to get a surface that you can do EBSD on, but have to keep in mind surface roughness and the angle will have an effect on the EBSD you collected. Now, we may do combinations of things. So for instance, with magnesium, sometimes we will do chemical mechanical polishing, or sometimes we'll do electropolishing, but we might follow it by some very light, low energy ion milling in order to remove the sort of thin oxide film on the surface. So sometimes you may have to use a variety of preparation techniques in order to get a good sample. Now, when we're talking about sample preparation, one of the biggest problems that people run into is they don't actually remove all the deformation damage in the preparation. So we end up seeing either poor patterns or actually no patterns because of the damage to the surface that's still present. So the black areas and the little dotted red lines represent the actual physical scratches on the surface. So if you only remove so much damage at sort of this level, it will look perfectly polished in a light microscope, but you will still have a lot of damage in the surface. You need to prepare the sample so you're down to this level in the material. So things such as cutting, grinding, and polishing can all introduce damage or can help take some of the damage away. But you have to keep in mind that you've got to do sequential removal of the damage down to a level where you're not getting a deformed region. Here you can see some argon ion milling of a pipeline sample. You can see we can actually sort of make out the crystal structure here. We're getting some orientation contrast. But we have this curtaining effect. You also see this in the fib as well on the sample. So we do have some topography but we are getting a very nice crystal structure exposed by the actual preparation technique. So you may have to do ion milling at 1 kV and then go to ion milling at a lower kV to see if you can reduce the amount of curtaining present. So sometimes your preparation and what you're doing will cause problems for doing EBSD. So in the case of coatings, we don't want to put a heavy metal coating on the surface. This will block the getting any pattern from the surface. So if you have any, if you have gold at any some sort of substantial thickness, you will not get any pattern from the material. You'll get patterns from the gold if it's crystalline. Even in the case of carbon coating, where you want to maybe reduce the charge because you don't want to have any drifting when you're collecting over a long period of time. If you make the carbon coating too thick, you can also reduce the intensity of the pattern that you're looking at. So you have to sort of keep that in mind. Low vacuum, sometimes you can use low vacuum to sort of reduce the charging from the material. This helps with drifting and things like that, but it will mean that your EDS, if you're collecting at the same time, will have a much larger spot size as a consequence of having a slight atmosphere in the chamber. Plastic deformation. So here you can see some polishing where we still have a lot of scratches. This sample did look perfectly polished, but because of the pores in the material, we run into a problem with debris coming out of the pores and causing scratches. So you have to be sort of careful about the choice of your preparation method. Maybe electropolishing would have been a better choice here. So you should be prepared to sort of switch methods or try different methods out to see if you can get better results on things. The material may easily oxidize, so you may have to basically prepare it and put it immediately in the SEM or put it immediately in some sort of protected atmosphere to prevent sort of oxidation, which will affect your results. Magnesium is very bad with this sort of problem. Even if you put it in a normal sort of desiccator, usually after a day, there will be even enough oxidation from the atmosphere in a normal desiccator that you'll get oxidation. Because we are using very high accelerating voltages and currents, we will get, in most SEMs, carbon deposition. So because of the various pumping systems used, you may have, and because you might be looking at mounted samples, you'll get organic material which gets cracked or broken down by the beam into carbon, which gets deposited over time on the sample. So sometimes this carbon deposition can be quite severe, so you may have to do things like plasma cleaning it off, especially if you're doing reanalysis of the same area multiple times. It's very important to clean the samples. So you can see over here, we can see little specks of colloidal silica all over the surface. So at high kV, usually the beam will go through the very fine colloidal silica, but you may see if it's thick enough that's giving a pattern or blocking some of the pattern that you're collecting. So you have to make sure that you clean off things here. You can see some scratches here, some deformation damage in the surface, which may not have been apparent when you looked at it in the light microscope. So, and you can see that our tungsten carbide particle has it's much more protruding than the rest of the material. So that can sort of be an issue as well. So most EBSD systems will have software for data processing, so you can produce, maps producing various sort of parameters, like showing you the orientation. So here you can see the orientation based on the Euler angles, or you look at grains, you look at recrystallization strain. You can collect kernel average misorientation maps. So all sorts of different sort of parameters based on the orientations and the misorientations between the orientation data points can be collected. You can also do sort of texture analysis, where you're doing sort of pole figures or inverse pole figures. So see a pole figure here from a particular plane, and we've related it to the acquisition surface, so the Z, Y, and X directions. Also, if you really like to get into mind-bending things, you can look at things in three-dimensional Euler space, so orientation distribution functions, and sort of look at different sort of ideal crystal structures and the relationships in the data that you have. So there are also tools available for data processing, not from the various manufacturers. So MTEX is a free MATLAB toolbox for EBSD. So very useful, a lot of things there. Allows you a little more freedom in doing things and adjusting things. And it's free, and they are doing development of new things and improving things there. So very useful sort of tool. France, you have the ATEX software. May not be, I'm not sure about availability to industry, but academia, there's usually no problem as long as they get acknowledged for the use of it. There is a method for analysis of patterns where you're taking simulated patterns and comparing them to experimental data. So a lot of mathematics involved in that and a lot of calculations. But that has been used to look at very poor patterns and actually determine orientations. EDAX, one of the companies that makes the EBSD hardware and software, does have a program for their data for looking at neighboring patterns and averaging and sort of re-indexing them, which can be very useful because quite often when you're collecting the data, you don't get sort of optimum data, or you may, in the case of when we're talking about the Oxford system, get zero solutions where you don't get any solution at a particular data point. So post-processing, quite often we may be adjusting the orientation data or filling in where we don't have any solutions or poor solutions. So one thing I will always recommend is that you make sure you save an original copy of your data somewhere in case what you do has altered things badly. So we can use algorithms to remove things like low-angle noise or average the orientation within a grain, all sorts of things like that. But one of the biggest things that's done, especially in the Oxford system, is we look at the nearest neighbors of a zero solution where we don't have results. So anything here you see with a black sort of dot. And we look at the surrounding pixels and substitute in that orientation for where we didn't have any results. So you can see that we get a very nice picture if we do this data substitution. So this, we're looking at the 6 nearest neighbors, and we did it, iterated it for 6 times to get this sort of result. Now, the problem with this is you can, if you do it too much, you can maybe, instead of getting an equiax grain, you might start to grow wings or things like, or different sort of directions off of your grain. So it won't really represent how the grain actually is. You also, and this is a very common thing to see in EBSD, this particular material, the reason it has so many zero solutions is actually because it has phases within it, within the grains and at the grain boundaries. So you are actually eliminating the places where you didn't get any results because there's a different phase there. So you will quite often see this in aluminum alloys, where you will just get a nice map of the aluminum, but all the basic precipitates and phases are ignored in the map. Quite often the case for that is because it's sometimes very difficult to actually analyze intermetallics because they're very hard to sort of prepare. So you might do something like ion milling to do that, but that comes along with its own sort of problems. Now, one of the maps that we can collect with the Oxford system is what's called a band contrast map. So this is actually looking at the patterns, not at the actual index data. So, and if you can see, it's probably very hard to see on the screen here. There are some zero solutions here which are sort of green, but kind of hard to see at this sort of magnification. But this gives you sort of an idea of the sort of quality of the patterns that you've collected. It also gives you sort of information about the sort of microstructure as well. So we can see where the prior austenite grain boundaries are. We can also see the different lathes that exist within the structure. So very useful sort of map for collecting information. Now, if we're talking about TKD, here we can see an aluminum film on magnesium. So we're getting a little problem of collection of data at the edge. There's probably a little bit of rounding there. So due to a change in sort of hardness, so we've maybe lost them there. Or it might be that there's an actual layer here, which is of different composition that we didn't account for in the data collection. So here we're getting inverse pole figure coloration to give us an idea about the orientation of the grains relative to the inverse pole figures. So we have both the HCP magnesium and the, I think it's FCC aluminum. So I'd like to acknowledge a few people here for their sort of contributions to things. So I'd like to acknowledge Oxford Instruments because a lot of information from them in the presentation. I'd also like to acknowledge Glynis de Silveira for lots of information and advice on things, as well as Scott Sitzman, Brewer and Michael from Sandia Labs, and from the CCEM, Hui Yuan, who provided the TKD information. Now, there are a lot of good references or sources for information. You can go to the Oxford Instruments website. The EDAX website also has a lot of resources and information as well. Quite good. They have quite a collection of papers. It's quite useful. One book I find very useful for if you're going to be doing sort of texture analysis, the book by Valerie Randall and Olaf Engler. It's a very good introduction to texture analysis. So a lot of information there. Valerie also did a very nice review paper where she talks about strategies for data acquisition and programming. Sorry, data acquisition and processing in EBSD. Humphreys did some nice information about resolution involving grain and subgrain characterization. He also did a program called VMAP for processing EBS data from cubics as well. Angus Wilkinson at Oxford has done a lot of work on strains for EBSD, so a lot of helpful information there. Here you're getting into maybe some cross-correlation analysis of things. So actually looking at the patterns and basically determining small shifts in the patterns in order to figure out sort of strain within the material. David Dingley is actually, I would classify as the sort of grandfather of EBSD. He did a lot of the initial sort of development work before the advent of computers. So video camera, collecting the patterns and indexing them. So thanks to him for this lovely technique. And from the Sandia Labs people, they did a nice article in Microscopy Today talking about the risks of cleaning using the data substitution method. Quite useful reading that. So thank you for your attendance. We'll do some questions if you like. And if we don't have time for the questions, you can reach me at butcher@mcmaster.ca. I have no problem answering questions that people have about EBSD and the preparation as well. Don't be afraid to email me. It might take me a few days to get back to you, so be a little patient, but I will answer your questions as best as I can, or I'll refer to you to maybe someone who can help you or suggest someone that might be able to help you. Thanks.
Great. So we do have some questions. So if you have any other questions that you'd like ask, please put them in the chat. But to begin, Chris, what is the typical depth which we can inspect with EBSD?
Okay, I didn't quite hear what you said there, Sam. What was the typical?
Depth.
Oh, depth. Well, it very much depends on the kV that you're using and also the material. So in something like, for instance, pure nickel at 20 kV and maybe a probe current around 10 nanoamps at a reasonable distance, like 15 millimeters of working distance, with the detector inserted in, you're probably about 20 nanometers is where you're getting the sort of main pattern information from. It'll vary a bit because we don't necessarily have a nicely coherent beam, so there's a little bit of energy spread in it. So, but generally it'll be from about that sort of depth. So heavier materials count on it being a little bit less deep. So things like gold, you're not going to be getting the beam going in so deep. Also, you have to remember once it's, you can have the effects of things bouncing around. So once it's no longer sort of reflecting or transmitting through the actual unit cell, you're actually not getting really any information. So that's what your background shows up.
Okay. Do we need coding in this technique?
If everything has a nice conductive path to ground and everything is nice and stable and you don't have charging because you have colloidal silica on your surface, or it's not, if it's mounted in plastic, sometimes you'll get influence from the plastic if it's not terribly conductive. Quite often we will on mounted samples, even if they are in a conductive mount, put a very light carbon coating on. So maybe 5 to 10 nanometers in order to sort of reduce the charging so we don't get sort of drifting effects. You can do, if you have a nice system, do drift correction, which will help out with drifting effects, whether they're mechanical or beam induced.
Another question. On slide 6, where is the position of the camera which sees and collects the live image of the Kikuchi lines on the detector?
Okay. So on slide 6, what was the question?
Where is the position of the camera that sees and collects the live image of the Kikuchi lines on the detector?
Oh, okay. Well, I mean, the phosphor screen is here. The camera's back here. We have it bouncing the backscatter electrons, and they're producing the pattern on the screen. So this is inserted in. So you're probably a distance of maybe at most 10 millimeters away from the sample. So you're in pretty close because you want to get a lot of signal. The further out you are, you saw the effects you have on sort of the area of the pattern you collect. But it's really, we want to get it in close so that we're actually collecting a very bright image, relatively. Otherwise, it's going to take us a long time to collect any substantial amount of data. Now, one problem we do have if the sample is further away, so this might be at a position of a working distance of 10 to 15 millimeters. If it's further away, we sometimes run into problems with the backscatter electrons actually producing X-rays that get collected in the EDS detector. So sometimes you'll run into problems with this arrangement, and you will actually start getting X-rays from the camera or the phosphorus screen.
Okay. And one last question. What is the effect of the grain size on the quality of the signal?
Well, the problem with the grain size is usually where the grain boundaries are. So you want to generally do a fine enough step size, assuming you have a field emission microscope to make a small enough spot that you can get enough data within the grain to sort of define it. So it tends to be the grain boundaries that are the problem. But you can also run into problems if it's a very deformed material. So in a deformed material, you may have more problems getting good patterns. So it might be hard to sort of identify patterns as well. So that's why we're very concerned with sample preparation, because we want to eliminate anything that's going to make the patterns worse when we're doing this sort of collecting. I hope that answers the question. If not, send me an email.